For a decade, the headline has been deep learning, but here's a secret the headlines skip. For most of the data businesses actually have spreadsheets, tables, rows, and columns. The classic algorithms still win. Deep learning didn't replace them, it joined them. We'll tour 10 of them: linear and logistic regression, k nearest neighbors, support vector machines and naive Bayes, decision trees, random forests and boosting, and two unsupervised methods, k-means and PCA. The real skill isn't mastering any one of them, it's knowing which to reach for. Start with the simplest model there is, a weighted sum of the inputs with no activation on top. Y hat equals W1x1 plus W2x2 and so on plus a bias. Geometrically, you are fitting the straight line, or in many dimensions, the flat hyperplane that sits as close as possible to every data point. And the beautiful part, you don't even need gradient descent. Calculus hands you the answer in closed form. Theta equals x transpose x inverse times x transpose y. It's fast, every weight is interpretable, but it can only ever capture straight line patterns. To classify instead of predict a number, take that same linear score and squash it through a sigmoid into a probability between 0 and 1. The raw score is the log odds. The sigmoid bends it into how likely is the positive class. The decision boundary sits exactly where that score is 0, a straight line. We train it with binary cross entropy. It's interpretable, fast, and the go-to baseline for classification. But like linear regression, it can only draw straight boundaries. K nearest neighbors is almost embarrassingly simple. To label a new point, find the K most similar training examples and copy their answer. A vote for classification, an average for regression. There's no training at all, it just stores the data. Choosing K is the whole game. A small k is jumpy and overfits to noise. A large K is smooth but blurs away real structure. The catch: every single prediction has to measure distance to the entire training set, so it scales badly. A support vector machine doesn't settle for any boundary that separates the classes. It finds the one with the widest possible margin, the biggest empty buffer between them. Formally, minimize 1/2 the norm of W, subject to every point landing on the correct side by at least 1. And here's the elegant part: only the points right on the margin's edge, the support vectors, actually fix the boundary. Move any other point and nothing changes. For curved data, the kernel trick lifts it into a higher dimension where a straight cut works without ever computing the new coordinates. It's superb on small, clean datasets, but scales poorly and needs tuning. Naive Bayes flips the question around. Which class makes the features we observed most probable? By Bayes' rule, that's proportional to the prior, how common the class is, times the likelihood of each feature given the class. The naive part is assuming every feature is independent given the class. That's almost never true. Yet it works because to pick the winner, you only need the classes ranked correctly, not the probabilities exact. Training is just counting. It's blazing fast and the classic baseline for spam and text. It simply ignores correlations between features. A decision tree plays 20 questions. It asks a sequence of yes or no questions about the features. Is income over 50,000? Is age over 30? Branching down until it's confident enough to answer at a leaf. It's built greedily, top down. At each node it scans every feature and threshold and keeps the split that makes the resulting groups purest, measured by Gini or entropy for classification, variance reduction for regression. A tree is trivially interpretable. You can just read the logic. But left to grow deep, it overfits badly, carving a tiny box around every single training point. One deep tree overfits, so grow many and average them. That's bagging. Train each tree on a different random resample of the data, then vote or average, and their independent errors partly cancel cutting variance. A random forest adds one more twist. At each split, each tree may only look at a random subset of the features. That stops one strong feature from dominating every tree and making them all look alike. Decorrelating them is what makes the averaging actually work. Forests are robust, need almost no tuning, and are one of the best off-the-shelf algorithms for tabular data, at the cost of being less interpretable than a single tree. Boosting takes the opposite tack. Instead of averaging independent trees, it builds them in sequence, each new tree trained to fix the errors the ensemble has made so far. Train a weak model, find where it's wrong, train the next one on those mistakes, add it in and repeat. Where bagging attacks variance, boosting attacks bias. The practical form is gradient boosting over decision trees, and three libraries dominate: XGBoost, LightGBM, and CatBoost. On structured tabular data, this often beats neural networks outright. So, if you're not sure what to try first, start here. Now, two unsupervised methods, no labels at all. K means partitions, the data into K groups of similar points. It alternates two steps. Assign every point to its nearest centroid, then move each centroid to the mean of the points assigned to it. Repeat until nothing moves. Under the hood, it's minimizing the total squared distance within each cluster. It's cheap and simple and works beautifully for round evenly sized clusters. But you have to choose K in advance, and it struggles with stretched or oddly shaped groups. Principal component analysis is unsupervised compression. Picture your data as a cloud shaped like a cigar. One long direction with lots of spread, one thin direction with almost none. PCA finds those directions, the principal components, which turn out to be the eigenvectors of the covariance matrix, ranked by eigenvalue. Keep the long directions, discard the thin ones, and project every point onto the top few. You get far fewer dimensions while keeping most of the information. It only finds linear directions though. For curved structure, reach for OMAP or TASNE. So, how do you choose? Match the tool to the shape of the problem. Tabular data and you need to explain it. Linear or logistic regression, or a shallow tree. Tabular and you want maximum accuracy, gradient boosting. Want a quick solid baseline, random forest, small clean data, an SVM, a text baseline, naive Bayes or logistic regression. What's similar to this? K nearest neighbors, images, audio or text at scale. That's where neural networks take over. Unlabeled and you want groups, K means. Unlabeled and you want to compress or visualize, PCA or UMAP for curved data. Here's the takeaway. Classical algorithms were not replaced by deep learning, they were joined by it. Deep learning owns the unstructured world, images, audio, language, but for the spreadsheet, the structured tabular data most businesses actually run on, gradient boosting still tends to beat neural networks. The honest answer to which algorithm is almost always, it depends on the data. Now you know how to decide.